In this class, we will discuss about some of the parameters which are used in the design of beam columns. Before that, we will understand what do you mean by first order and second order moments. Actually, when in the case of any structural member, different types of loads will be acting. So one is the transverse load. Transverse load means the loads which are acting perpendicular to the axis of this member. Another is axial loads. So axial loads, as you know, they act along the axis of the member. So the moments which are developed due to transverse loads, they are called as primary moments. So these like this primary moments. The moments which act due to lateral loads, they are called as secondary moments. So these are the primary moments, these are the secondary moments. But what happens in the case of beam column, since it is subjected to both bending and axial load, we have to consider the effect of both the bending and axial load, that is primary moments as well as secondary moments we have to compute in the case of beam columns. And the net deflection, total deflection will be deflection due to transverse load plus deflection due to axial load. So the maximum bending moment in such a case, in case of beam columns, it is actually nothing but moment amplification factor or interaction factor K into maximum bending moment due to flexion. That means whatever maximum bending moment you are going to get due to this transverse load, that is the bending moment due to flexion, that has to be multiplied by an amplification factor or an interaction factor called K to get the maximum bending moment due to the effect of both these two, primary as well as secondary moments. Now, if you take two examples, in first example, the member restrained against side strain. If the member beam column is restrained against side strain, then the deflection will take a shape like this. Maximum deflection will be here, that is delta. Suppose in the case of unbraced systems or unbraced frames, this is a column in unbraced frame. So in such a case, maximum deflection occurs at the free end, where there is no bracing provided or the lateral movement is not restrained. So in that case, it is capital delta. So here, this P to small delta, whatever is there in this case, this is also due to the member effect, whereas P into capital delta, this is called due to the structure effect. These are the additional moments which we have to calculate in the case of beam columns, and these additional moments, secondary moments, should be added to the primary moments to get the maximum bending moment. So, in the design of beam columns, we have to understand that there will be two types of moments. One is primary moment and another is the secondary moment, and the net moment or the maximum moment will be the combination of both those two moments along with that magnification factor. Now, before going to the design, we will understand two types of curvatures in the beam columns. The first one is how the moment will develop in the case of a single curvature. So, moment magnification for column bent in single curvature. So, this is how a column bends. If the curvature exists only on one side, so this is called as a single curvature. So, you can observe here one important thing that this m value, whatever develops here, they may be equal or unequal, irrespective. So, the m, they are called as the end moments. You can call them as end moments. So, these end moments, if they act in opposite directions, you can see here, this is anti-clockwise, this is clockwise. Suppose I have taken equal values. If they act in the opposite direction, then the single curvature effect will be there. In that case, this is the primary moment, this is the secondary moment. So, along the length of the column, if you plot the bending moment diagram, primary moment will be uniform like this, whereas secondary moment will be P into delta at somewhere here, and it will be 0 at the ends of the column, because the delta is 0 here. So, there will be P into delta will be 0 here, P into delta will be 0 here, and here it is P into delta, and the maximum bending moment occurs here, of course here. So, M max will be in this case M plus P into delta. So, this is the resulting bending moment diagram. Maximum bending moment occurs here. This is in the case of a single curvature. So the end moments act in opposite directions may be equal or unequal, irrespective. The second type is the double curvature. In the case of double curvature, if the moments act, end moments act in the same direction, you can see here, this is anti-clockwise, this is also anti-clockwise. So in such a case, the curvature will be on both the sides, that is called as double curvature. So if Pmax is the load, corresponding load, maximum load that the column can take, then the primary bending moment diagram will be like this, it will be 0 here, and the secondary bending moment diagram will be like this. So here what happens, this is the diagram for Pmax into delta, and this is the diagram for M. So please note that M is 0 here. And the net bending moment diagram, combination of these two will be something like this, where the maximum bending moment occurs somewhere here, at this point. So if you add this and this plus this is this value, this plus this is this value. But you have to note down that here one important thing, the maximum moment will not be equal to M plus Pmax into delta, whereas that exists in this case. So maximum bending moment is M plus P into delta in this case, in the case of single curvature, whereas in the case of double curvature, it is not equal to M plus Pmax into delta. So this is about the magnification of moment in both single curvature as well as double curvature. Please observe here the moments are in opposite direction, whereas here the end moments are in the same direction. Next, coming to, of course, for the design of a beam column, finally we are interested in finding the maximum bending moment. Maximum bending moment in a beam column, it depends on bending moment distribution within the member. So that means along the length of the member, how the bending moment distributes is distributed. That is the main factor for calculating the maximum bending moment. So we are going to use one important parameter called CM. It is called as equivalent moment factor or moment reduction factor or modification factor. So all these three are same. So the meaning of this is, significance of CM is, it converts any end moment configuration to an equivalent uniform or constant moment along the length of the member. So whatever may be the end moments, may be equal or unequal, may be clockwise or anti-clockwise. So this CM factor, it converts that end moment configuration to an equivalent uniform constant value of moment along the entire length of the member. So it is a function of psi and Pu by PCR. So it is a function of two things. One is psi. Psi is nothing but it is the ratio of MA to MB. So taking MB greater than MA, so this value becomes less than 1, or at the most it can be equal to 1, like this, or it can be between 1 and minus 1 it will be. So this pi value normally lies between plus 1 and minus 1. So later on we will see how to, just you have to take the ratio, take the higher value in the denominator, lower value in the numerator, take the ratio, and of course this psi, how to take plus or minus I will tell you. So here if MA is equal to MB, then this psi value will be equal to plus 1 or minus 1. Okay, so that is the maximum or minimum value. So PCR is nothing but here Euler's critical buckling load. Of course it depends on the end conditions, as you already know in your strength of materials. So Pu is called is the factor load. So you have to take the ratio of Pu by PCR. So this CM, that is the equivalent moment factor, depends on these two things, psi and Pu by PCR. So here MA, MB, if I take like this, moment at A, moment at B, the ratio I have to take, and I have to corresponding I have to calculate this psi. And the CM values you can get from the code book. So here for the beam analysis and design, beam column analysis and design, we have to refer pages 70, 71, 72 of IS 800 2007. Now how to choose the value of psi, whether it is positive or negative. It can be positive or it can be negative. So suppose if the moment distribution is something like this, it is something like this. So you have to take positive value of psi. That means what you can say here is, if here this end Mmax is anti-clockwise here, M minimum is clockwise. That means they are of opposite nature. So if these two are opposite nature, which can happen in the case of single curvature bending here, it can happen here in the case of single curvature bending. So then your psi value will be positive. If suppose M max and M minimum they are acting in different directions, opposite directions, then you have to take negative value of psi. That means what I mean to say here is, suppose if MA, I will give an example. If MA is equal to 10 kilonewton meter, MB is equal to 20 kilonewton meter, let us say. MB I have taken greater than MA. So the ratio MA by MB will be equal to 10 by 20, that is 0.5. So this is the value of psi. But if both are, please understand here, if I take positive side, these two should act in the opposite direction. Let us say MA something like this, MB something like this, then psi will be 0.5 plus 0.5. Okay? If MA is acting, MA and MB, if they are acting in the same direction, then psi will be equal to minus 0.5. So that's all. Okay? So this is a numerical value I have to take depending on whether MA and MB are acting in the same direction or same nature or in different directions or different nature. We have to decide the value of psi as positive or negative. So psi is positive if they act in different directions. Psi is negative if they act in same direction. You have to understand that. So if one is clockwise, other is anti-clockwise, irrespective of the ends, then psi value is positive. If both are positive, if both are clockwise or both are anti-clockwise, then psi value has to be taken as negative. So these values, these things we are going to use in the design procedure. So one is single curvature bending, another is double curvature bending. So you have to refer the page number 70, 71, 72, tables 17 and 18, which are given in those pages only for the design of beam columns, and it is in class 9.3. It is written as combined axial force and bending moment. So these are the pages we have to use for the design of beam columns. So here what I mean to say is, so there will be two types of moments in the case of beam columns, primary moments and secondary moments. One is due to transverse loads, another due to axial loads. The total deflection or the total moment or the maximum bending moment depends on these two effects of both transverse and axial loads. And you have two types of curvatures, single curvature and double curvature. And this factor, whatever this factor, equivalent moment factor Cm is there, it depends on one parameter psi and another ratio Pu by Pcr, which you can get from the code book. And the values of psi may be positive or negative. If the end moments are acting in opposite direction, then psi value is positive. If the end moments are acting in the same direction, then psi value is negative. So in the next class, we will see how we can design a beam column.